Hello and welcome to controllersTech. This is the third video in the STM32 Ethernet series using the Mongoose library. In the previous video, we used the Mongoose wizard to create web interfaces, and also covered how to link interface elements to STM32 components for functional integration. Today we will create a project involving the Mongoose library. We will create a simple weather station, which will log the temperature, pressure, and humidity data to the web interface. I will use the sensor BME280 for the measurement, as it can measure all these three parameters. We will also see how to use the graph feature of the web interface to display the data over a period of time. Before diving into the project, let's briefly review the features and capabilities of the Mongoose library. Mongoose is a network library for C++. It provides event-driven non-blocking APIs for TCP, UDP, HTTP, Websocket, MQTT, and other protocols. It is designed for connecting devices and bringing them online. On the market since 2004, used by a vast number of open source and commercial products, it even runs on the International Space Station. Mongoose makes embedded network programming fast, robust, and easy. The Mongoose wizard simplifies the creation of professional interfaces without requiring design or front-end expertise. It supports user authentication with multiple access levels, which can be enabled effortlessly via a single checkbox. Additionally, dashboards are kept up to date with a built-in device connection indicator on the toolbar. UI controls such as drop-downs, toggles, and inputs can be easily mapped to C structures by adjusting getter and setter functions. Conditional display functionality allows data exceeding predefined thresholds to be highlighted using alternative styles. Moreover, Mongoose provides seamless firmware update support for microcontrollers like STM32, ESP32, and others, requiring no additional configuration. Let's start this tutorial by creating the web interface first. Click on this button, Start Building Web UI. I have already created a basic UI. It includes the gauges for temperature, humidity, and pressure data, and the graphs for all three values as well. Now we will add the REST APIs to these widgets. I will use the Websocket to update all the gauges. Let's enable the Websocket in the settings. The gauge has a default range from 0 to 100. We can change this as per our requirement. For example, I am assuming the temperature might vary from -20 degrees to 50 degrees Celsius. That is why I have defined the ticks here to display all the possible variations on the gauge. Humidity can vary from 0 to 100%. So I will leave the range to that. Here I am adding the ticks to display the interval on the gauge. Finally, we have the pressure gauge. The pressure is in kilopascals, and I believe it can vary between 90 kilopascals to 110 kilopascals. Now we will add the REST API for the gauges. Let's name the API endpoint as gauge. Now we will add three data fields for temperature, humidity, and pressure. I am keeping the variable type as integer for now, but we will change it later in the code. As I mentioned, I am going to use the Websocket to send the data to the gauges, so let's change the API name to Websocket. Now go to the page content, and change the API variables for all the gauges. We can test the Websocket API by sending the values to the respective data fields. You can see the values are displaying fine on the gauges. Let's see the graphs now. The graph does not display on its own, instead we need to define the values to display them on the graph. Let's create a new API endpoint. I am calling it temperature graph, and setting the data type to custom. Here we need to send a JSON response, which will then plot on the graph. The response consists of two entries, which will make two axes of the graph. Here I am going to plot the graph for temperature over a period of time. The time data should be the timestamp, which you can get from some website. The second entry should be the temperature data for the respective timestamp. The graph will not display the accurate data for a single value, hence we need at least two values. I am setting the second timestamp 100 seconds higher than the previous one. Finally, enclose both values inside a bracket. We have now prepared the JSON response for the temperature graph. Let's go back to page content, and set the API variable to temperature graph. You can see the graph is now displaying two values, and their time is approximately 1 minute apart. Let's create more API endpoints for the other graphs as well. I am setting the same values for others as well, we will modify them in the code itself. Let's change API variables for the respective graph. We will use the heartbeat to auto-update the web UI every few seconds, so the graphs can update accordingly. We will implement it in the code, but here set this auto-update interval higher than 0. Also enable the SNTP client to synchronize the time with Google's server. This will help us get the timestamp data for the graph. To use the SNTP, make sure the development board can access the internet. You can do that by connecting the dev board with the router, instead of directly connecting it to the computer. That is all for the designing part, let's generate the project. Now open the Cube IDE, and import the generated project. Here is the main file of the project, and the Mongoose folder contains all the Mongoose related files. Let's open the Mongoose configuration file. I do not have access to the router, and therefore I have connected the board directly to the computer. The board cannot use DHCP, therefore I am setting the static IP in the configuration file. Let's build the project once. We do not have any errors, so let's flash it to the board. Alright, now open the IP address in a browser. You can see the web UI is loading just fine. Right now the default values are being shown on the UI, but we will update them in the code. I want to update the gauge values every 5 seconds, and therefore I will use a timer to generate an interrupt for the timing. I am going to use the timer 6 for this purpose. Let's take a look at the device datasheet to understand the timer clock. Search for timer 6 in the datasheet. Here you can see the timer 6 is connected to the APB1 bus. If you see the clock configuration, here the APB1 timer clock is at 200 MHz. This means that the timer 6 clock is also at 200 MHz. If I set the prescaler to 20,000, and the auto-reload value to 50,000, the timer clock will be 0.2 Hz. This will enable the timer to generate an interrupt every 5 seconds. Make sure to enable the interrupt in the NVIC tab. Let's generate the project again to implement the changes made in the CubeMX. Inside the main function, start the timer 6 in the interrupt mode. Once the timer period is reached, an interrupt will trigger, and the period elapsed callback will be called. We will write all our code inside this callback function. As I mentioned earlier, I will use the Websocket to update the gauges. I have already explained in the previous video about how to use the Websocket to send the data to a particular element of the UI. Basically, a Websocket message consists of the keys and their values. We can use the Websocket handler to send these messages to the UI. We also need to add the Websocket handler in the main function. We want the Websocket to send a message every 5 seconds, so update the time here in milliseconds. Also, I am calling the handler as my WS handler. Let's define the temperature, humidity, and pressure variables. These variables will be updated based on the data received from the sensor. Here is the correct format to send the data to the gauge. Remember that we defined the data field temp, hum, and pressure in the WebSocket API endpoint. Here I am sending the float data for the temperature, humidity, and pressure variables. We will test this part first. Since the BME280 sensor is not connected right now, I am going to simply increment the variables inside the timer callback. This arrangement will increment the variables every 5 seconds, and the WebSocket handler will then send the updated variables to the UI. Let's build and flash the project to the board. You can see all the gauges are showing the value 1. Now after 5 seconds, the values are incremented to 2. So the WebSocket is working fine, and the data is being sent every 5 seconds, just as we wanted. Now we will make the graphs work with the test data. Let's define a few more variables first. For the testing part, I am going to plot the graph every minute, and the data will be retained for an hour. The temperature array will store the temperature data every 5 seconds, and this way it can store a total of 12 values in a minute. Once all 12 values are accumulated, we will take an average of them, and store it in another temperature array. This array will store the average temperature data for every minute, and it will do it for an hour. Note that this is an array with 2 columns, so we will use the first column to store the timestamp, whereas the second column will store the averaged data for a minute. This matrix will be used by the graph to plot the temperature data with respect to the time. I have defined similar arrays for humidity and pressure as well. The variable, index 5 seconds, will keep track of how many 5 seconds ticks have been passed, and the variable, index 1 minute, will track the 1 minute ticks. Let's write the code inside the timer callback function, which is called every 5 seconds. Initially we will fetch the temperature, humidity, and pressure values from the sensor. Then we will store these values in the respective arrays. The storing will start from the 0th element, of course. After storing the pressure data, the 5 seconds index will increment. This index variable will keep incrementing each time the timer callback is called, that is, every 5 seconds. When the value of this variable reaches 12, it means that 1 minute has been passed. Now we need to take the average of all the accumulated values in the array. So we will first add all the values, and store the result in the sum variable. And then calculate the average, by dividing the sum by 12. This averaged data will be stored in the matrix we defined above. Here we will use the 1 minute index to store the data into the matrix. The first column of this matrix will store the timestamp. The function mg now returns the timestamp in milliseconds, therefore I am dividing it by 1000, so as to convert it in seconds. If the SNTP is enabled, the function mg now will return the current time as per the Google server. However, if the board is not connected to the internet, this function will return the time since device boot. The second column of the matrix will store the averaged data we calculated just now. Once all the storing is done, we will reset the 5-second index variable. Also increment the iMinute index variable, so the next data can store in the next row of the matrix. I am storing the data for 1 hour, therefore I am resetting the variable after it reaches the value 60. That is all we need to write in the timer callback. Let's open the Mongoose glue source file to further link this matrix data to the graphs. These functions are pre-generated by the dashboard for the use of graph. We have 2 ways to deal with these functions now. Either we can make the changes here in this file itself. But let's say we make some changes in the UI, and then integrate those changes into this project. This will overwrite this entire file, and we will lose all the changes we made in this file. We can prevent this by using the second method. Copy the generated function from this glue file, and paste it somewhere in the main file. Now change the function a little, for example, change the word glue with my. I am modifying the temperature here to prove that this method works. The temperature now changes from 0 to 30 degrees. Now before the run Mongoose function, call the function Mongoose set HTTP handler. Here we need to provide the name of the API endpoint, which for the temperature graph, I have defined as temp graph. Also set the function for this endpoint. Now let's build and flash the project to the board. Any changes in the UI will overwrite the glue source file, but since we have defined a separate function for the temperature graph, it will not be affected. You can see the temperature is changed from 0 to 30 degrees. This is the same as we defined in the new function, whereas the other graphs still shows the default data. So this way we can write separate functions outside the glue source file. The graph is a custom data type, hence there was only one function. Different REST API endpoint types use different callbacks. You should define all the functions generated for a particular endpoint. Since I am not going to regenerate the UI, I will continue writing the code in the glue file itself. Let's include the main header file first. Now we will define the matrix arrays as external variables. Let's also define the 1-minute index as an external variable here. The function tempData will be used to fetch the data from the matrix, and convert it to the JSON format required for the graph. We will extract the values from both the columns of a row, and convert them into this format. Note that the values are separated by a comma, therefore I have defined separate conditions for the first data, and the rest of the data. Here the comma is also included in the conversion. The first value is the timestamp, whereas the second value is the temperature data. Let's remove this part from the reply function, as we will fetch the data from the temp data function. The data still needs to be enclosed in a bracket, so let's put brackets here, and the format specifier should be pass the temp data function here, and also pass the HTTP message structure. We will do the same for humidity and pressure data as well. That is all that we need to modify in the glue source file. Now we need some way to refresh the UI every 1 minute, so the graphs can update in the UI. I mentioned it in the beginning, Mongoose Heartbeat is designed for this purpose. Even though we have set the auto update interval here, we still need to call the glue update state inside the code. We can do it inside the timer callback function itself, but in order to make it an independent operation, I will use Mongoose timer to do so. We need to add the timer, after the Mongoose library has been initialized. Let's add it here in the run Mongoose function. I have set the timer to run every 60 seconds. Basically it will call the function, auto update timer, which we will write in the main file. Inside this function, we will call the glue update state to refresh the entire UI. Let's build the project. There is an error in the pressure graph function. Actually there should be pressure here. Let's build it again. All the errors are gone now, so let's test the project. You can see the gauges are updating every 5 seconds. I am fast forwarding the video, so that we can see the graphs update. After 1 minute, the gauge values are 12, and we have an initial value on the graph. The value is the average of all the 12 values, hence it is 6.5. The x-axis of the graph will not show correct data until there are at least 2 readings on it. Let's wait for another minute to see the next reading. Now the gauge value is 24, so 2 minutes have passed. We have a second reading on the graph, which is an average of values from 13 to 24, that is, 18.5. Also note the time axis. I don't have an internet connection to my dev board, since the board is directly connected to the computer. Therefore the function mg now returns the time since boot. It starts showing the time from 0100 hours. The first reading is a minute after the boot, while the second reading is after 2 minutes. Now we have got the third reading after the third minute. So everything is working fine, and now it's time to integrate our sensor into this project. I am using BME280, as it can measure all three parameters together. I have already covered a tutorial explaining how to make this sensor work with STM32. Therefore I am not going to explain it again. Here I will simply use the library files from the previous tutorial. Let's open the downloaded project. Copy the BME280 STM32 source file inside the source folder of our project. Now copy the header file inside the include folder of the project. Now open the main file. Here we need to define the variables to store the measured data. We have already defined these in our project. We need to copy this function in our main file in order to initialize the sensor. And finally BME280 will be called each time to measure the data. Let's copy the initialization function inside the main function. Also include the BME280 header file. Now inside the timer callback function, we will call the measure function to measure the temperature, humidity, and pressure data. The pressure data returned by the function is in pascals. But I have designed the web UI to display the data in kilopascals. Therefore I am dividing the pressure value by 1000 here. Let's build the project now. We have an error in the BME header file. Let's change this to the main header file. We still have errors in the project. BME280 works with the I2C, which I haven't enabled yet. Let's open the schematics of the H745 Discovery board. I am using this STMod extension that comes along with the board itself. Here you can see the I2C data pin is PD13, and the clock pin is PD12. Now go back to the CubeMX, and search for PD13. It is the I2C4 data pin. Similarly, the pin PD12 is an I2C4 clock pin. Let's enable the I2C4 now. I am leaving everything to default, so the I2C clock is at 100 kHz. That is all we need to enable here. Click Save to generate the project again. Now open the BME280 source file, and change the I2C handler to I2C4. Let's build the project again. There is still an error left in this source file. Let me change this to BME280 I2C, so it can directly get the data from the definition. Alright, everything is fine now. Let's flash the project to the board. Wait for the UI to sync with the board. Now we have the actual data from the sensor. The temperature is 28 degrees Celsius, relative humidity is 56.6%, and the pressure is 94.7 kilopascals. I am fast forwarding the video, and you can note the graph data. These are just the 3 readings captured on the graph till now, and they are accurate. Here is the picture showing the accumulated data for an entire hour. So our weather station works fine. But the data displayed on the graph is only for an hour. We can make a few changes to record the data for an entire day, an entire month, or even for a year. I will demonstrate the changes required to keep the data for a day. I will record the average data for an hour, and display it on the graph for a day. Let's adjust the arrays first. Now we want to take the average for one complete hour, so we need to record at least 720 values, each value at an interval of 5 seconds. Since we are keeping the data for only one day, there will be only 24 rows in the matrix. Each row represents the average data for 1 hour. Let's change this index to 1 hour. We will start taking the average once all 720 values have been captured. So let's change the 12 to 720 everywhere. Also change the 1 minute index to 1 hour index. And this index will reset once the value is reached 24. We need to make these changes in the Mongoose glue source file too. Also change the index variable to 1 hour. That is all the changes we need to make. Let's build the project now. There is one thing left in the Mongoose glue header file. The MG timer is still configured to run every minute. Let's modify it to run every hour, so that the UI updates once every hour. Alright, let's build and flash the project to the board. I cannot run the video for hours to show the changes, so here is the picture showing the data for 10 hours. You can see the reading on the graph displayed every hour. So this way we can log our weather data into the UI. You can even increase the array sizes to log the data for an entire month. So we saw how to use the Ethernet using Mongoose library to create a weather station. We will continue with another project in the next video of this series. This is it for the video. I hope the concept was clearly explained in the video. You can download the project from the link in the description. Leave comments in case of any doubt. Keep watching, and have a nice day ahead.